So we will start with the second problem. You will see here the drawing. It is a double pane glass window. It's kind of enclosure. We discussed the enclosure actually in the household. We use the double pane window to prevent the rate of heat loss, because in between two glass we got the air as an insulator. So we discussed during the lectures. Let's forget about it. So we know the height, 0.8 meter height and 2 meter wide double pane window, and it consists two sheet which is separated by 2 centimeter thickness air gap. And we know the temperature for the double pane window, for two different sides is 12 and 2 degrees centigrade. We need to calculate the rate of heat transfer. So if we start with this problem, actually our ultimate target is we want to calculate the rate of heat transfer, and the Newton's law of cooling. This is the AS, and the temperature difference delta T. Let's say T1 and T2 from two different sides. So what we know this temperature difference T1 and T2, but we need the area, the surface area. So the surface area, it is a rectangular one, so we know the height and the weight. It should be the area. Then we need the heat transfer coefficient. So if we want to get the heat transfer coefficient, we need the Nusselt number. Nusselt number correlations for natural convections. We need to think about the aspect ratio, the aspect ratio of the geometry, that means the height and the length, because depending on this aspect ratio, there will be different Nusselt number correlations for different problem. Also, we need to know the Rayleigh number, right? We need to know the Rayleigh number because this is important when you will select the correlations. The other thing we need to know is the characteristics length. That's also important. So this will be the total flow charts. If we want to solve this question, it is actually the total flow chart we need to follow. And we have the system is like this. So here, let's say it's like this. So we got air at this position with a gap 2 centimeter. Yeah. So, and we know this, it is 0.8 and it is 2 meter wide. Okay, 2 meter wide. So yeah, that's actually the wall information we know. All right, so what we will do now, we'll write down the assumption as usual, what we did so far. So the assumption, I'm not writing here, it is steady conditions and air is ideal gas. We're not going to consider any radiation heat transfer effect, but we need to calculate the properties. Okay, so the properties is we need the properties at the film temperature is the average temperature. So it will be the T1 plus T2 over 2. T1, let's say just one side of the glass, the other side is T2 over 2. So that means it is 8 degree. It is 7 degrees centigrade. So the material is air. So now we will use table A15, and at 7 degrees centigrade temperature, we know the thermal conductivity is 0.02416. Viscosity 1.4 10 to the power minus 5 meter square second. Prandtl number 0.7344, and the heat, the volume expansion coefficient, that means the average, let's say average temperature. So it is 280 K. How it is 280 K? 7 plus 273. So 280 Kelvin. Okay, all right. So now when we will start with the analysis, guys, I discussed during the lecture, you can remember for an enclosure, it is always filled with the air. So for rectangular enclosure, we can use the space between two glasses. So that air gap, we can use that distance as the characteristics length. In some cases, you can use this as a characteristics length as well. But once you know this gap, so you can use this as the characteristics length. So let's say the characteristics length characteristic length LC, it is equal 0.02 meter. It is 2 centimeter. We convert it into meter. Now Rayleigh number. So the Rayleigh number, we need to select the the Nusselt number correlation. The Rayleigh number for this is G beta T1 T2, and the characteristics lines for the viscosity square and Prandtl number. Alright, so this is 9.8 and it is 1/280. It is 12 minus 2, and LC is 0.02. Sorry, 0.02 cube over viscosity is 1.4 and 10 to the power minus 5. This is a square. Prandtl number 0.7344. So if we simplify this, we will get it is 1.050 and 10 to the power 4. This is our Rayleigh number. So I showed you all the theories, especially for the Nusselt number correlations for different combinations. Like when we'll select the Nusselt number correlations, if you see the flowchart here, we did the Rayleigh number and the characteristics lines. So if we want to get the Nusselt number correlations, we actually need to see the aspect ratio of the domain, because for different aspect ratio we have different Nusselt number correlation. So the aspect ratio for this problem, it is the ratio, it is the ratio of the height and the length, height over L. So height is equal 0.8 and the characteristics length is 0.2. So we got it is 40. So we know from the theory, when the aspect ratio is 40, then we can use this Nusselt number correlation. It is 0.42. Rayleigh number is 1.4 power, and the Prandtl number is 0.012 H over L, and it is negative 0.3. So this is we know from the literature, like we discussed it during the lecture. So for future reference, it is actually the equation of the correlations number 9.54 from your SI unit 5th edition book. Okay, so what we can do now, we can substitute the value. The Reynolds number 1.05 and 10 to the power 4, its power 1/4. Prandtl number 0.7344 and power is 0.012, right? And the aspect ratio, I can say it is 40 and negative 0.3. So we will get the Nusselt number is 1.4. Important discussion here. You guys know from the theories when I discussed, we said we got from the literature that Nusselt number equal 1 for an enclosure. That means it corresponds that it will be pure conduction heat transfer through the enclosure. If the Nusselt number is equal 1, we discussed, then it will be pure conduction. Okay, the air in the enclosure will remain closed, but no natural convection current will occur for when the Nusselt number is 1. Here we got the Nusselt number is 1.4, which also indicates that it is actually pure conduction. Okay, heat transfer is happening by pure conductions, and it is the increase of the heat transfer. Increase of the heat transfer due to the natural convection current that could develop in the enclosure. But here, okay, so we'll discuss that on maybe later on. So Nusselt number is 1.4, but what we know, if it is Nusselt number is 1 equal to 1, that means it is pure conduction heat transfer and no natural convection current will occur inside the enclosure. So now we got it is 1.4, just slightly higher than that value. All right, so once we got this Nusselt number, then we can calculate the the heat transfer coefficient from here. But for this question, maybe we can do something different. So now let's calculate the surface area. Surface area, it is the height and the void. So it is 0.8 and W is 2 meter. So we will get it is 1.6 meter square. So now the heat transfer. Heat transfer Q, it is equal. We say Haze is T1, T2. So it is the Haze equal, we know from the Nusselt number definition, we can write it is Haze equal the thermal conductivity, okay, and the Nu. Can we do it? Can we write it like this? Yes, we can. KNU from the, so you will see from the theories we discussed. So we can write it like this: Haze equal K into thermal conductivity and the Nusselt number. This is the surface area, T1 minus T2. So the thermal conductivity here is 0.02416. Nusselt number is 1.4 and the surface area is 1.6. It is 12 minus 2 over 0.02. So the rate of heat transfer, it will be 27.1 watt. Okay, so what we got from the formula is it is actually 27.1. So what I was trying to tell you previously, actually the Nusselt number for our case in this problem we got it is 1.4, which also indicate that the enclosure is 1.4 times that by pure conductions. Okay, so if it is 1, then it is just pure conduction, but it is 1.4 times that by pure conductions. So that's actually the solution of this problem. You will see here we calculated the characteristics lengths, then Reynolds number, then the aspect ratio, Nusselt number. Here we didn't calculate the Haze in usual ways, but we write down the formula there. Then we got the surface area and then we use the formula here.